That's a good point. This was just like the long wire I did up here, where I had an H, right? The height of the cylinder came into play right here. And then we said that our answer shouldn't depend on some arbitrary height that I chose for my Gaussian cylinder. You might have chosen a different height, right? So what ended up happening was the charge enclosed inside of my Gaussian cylinder, if I double my height, I've doubled the amount of charge I enclosed inside my cylinder, right? That's what happens here. Now I have charge per area, right? So if this cube has a big cross-sectional area that's intersecting a big piece of this sheet, I'm going to have a lot of charge enclosed, but I'm going to divide by a big area. And if this purple section, the Q in is much smaller here because it's a smaller area, I divide by a smaller area, and sigma is always the same. Let's look at shielding one more time. We did it briefly at the end of the last class. So we said that we're sort of trying to picture what's going on inside of a conductor. And if we had a region of space that initially looks like this, has a nice uniform electric field left to right across it, and then we put a conductor in there. Doesn't matter. Circular conductor. Let's just make it a solid. Then what happens? Our electric field, what's the definition of a conductor? Charges free to move around. If the charges are free to move around, the electrons are free to move around, and we put it into a big electric field, those electrons are going to feel a force, right? And they're negatively charged, so they go the opposite direction of the electric field. So if the electric field's pointing to the right, the electrons are going to get pushed to the left. The first electron that moves only sees a force pushing it to the left. And so it comes over here, and it leaves a positive behind, right? It was shielding that positive, it was hanging right next to that positive, but it moved now to the other side because it's in an external electric field. The second electron says, oh, this external electric field is pushing me to the left, but there's already an electron over there that's repelling me and pushing me back, but the external electric field is stronger, so I'm going to the left. Ends up over here, leaves a positive charge behind. The third electron does the same thing. The fourth electron does the same thing. The fifth electron does the same thing. Actually, there are lots of them, but you get the idea. Then the next electron says, wait a minute, the external electric field is pushing me to the left, but the internal field caused by these electrons and positive charges that have separated out is pushing me to the right, and it's exactly equal and opposite to the external field, so I'm not moving. I'm just going to stay where I am. And the electrons keep moving until that situation comes up, right? They keep moving until they say, oh, wait a minute, there's no force on me. I'm going to stay where I am. So that always ends up being the final situation. You put a conductor in an electric field. Eventually, it happens pretty quickly, actually. Enough electrons move to cancel out the external field. And so inside the conductor, you always end up with E equals 0. Gesundheit. And so what do you have? Your external field was coming along here, and it terminates on that negative charge, and then it picks up again on that positive charge. And so our electric field looks something like that. And inside the conductor, the electric field is 0, because the field from the external source and the field internally due to the charges that have moved exactly cancel out. We always get 0 electric field inside of a conductor. This was a solid conductor, but if we had made it hollow, the same thing would happen. Okay? And inside both, in the conductor and in the hole, E would be 0. The only way you can get an electric field inside the hole, inside the cavity of a conductive shell, is if you have a charge in there. Okay, that's the only way. It's not going to come in from the outside. It's going to be shielded from any electric field from the outside. You have to put a charge into the cavity in order to get an electric field inside the cavity of a conductor. Okay?